Welcome all. I am A.R. Manjuladevi, Assistant Professor, Department of EEE at JJ College of Engineering and Technology. Today I am going to present a video lecture on Digital Logic Circuit, subject code EE3302. Now we are going to see about sequential logic latches and flip-flops. These are the subheadings: Introduction, Memory Elements, Pulse Trigger Latches, Edge Trigger Flip-flops, and Asynchronous Inputs. Let us see in detail about the introductions of these sequential logic latches and flip-flops. A sequential circuit consists of a feedback path and employs some memory elements. The sequential logic circuits is nothing but it is a combination of combination logic and memory elements. The external inputs are given to these combination logics and the output of combination logic is given back to memory elements. Then the output of memory elements is given back to combination logic as a feedback. The combination logic's outputs are called combination outputs. The memory elements output are called memory outputs. There are two types of sequential circuits. One is synchronous and another one is asynchronous. In synchronous, the output changes only at specific time. In asynchronous, output changes at any time. Multivibrator. Multivibrator is a class of sequential circuits. They can be classified into bistable, monostable, and astable. Bistable logic devices are latches and flip-flops. Latches and flip-flops differs only in the method used for changing their state. Next, memory element. Memory element is a device which can remember value indefinitely or change value on command from its inputs. This is the logic diagram of memory elements. The input is given as a command to memory element. The output value is stored in stored value. This is the characteristics table of memory element. In inputs is set can be either 1 or 0. Output should be 1. The input is reset can be either 1 or 0. The output should be 0. In no change condition, the given input is same as the output. If the given input is 0, then the output is 0. If the given input is 1, then the output is 1. Memory element with clock is known as flip-flops. The flip-flops are memory elements that change states on clock signals. This is the logic diagram of flip-flops. The logic diagram is same as the memory elements, only the clock signal is added to the memory element. This is the timing diagram of this memory element. The rising edge is known as positive edges. The falling edge is known as negative edges. There are the two types of triggering or activations: pulse triggered and edge trigger. In pulse trigger, it's contain latches. In latches, on is 1, off is 0. Next, the edge trigger. Edge trigger contains flip-flops. In positive edge trigger, on is 0 to 1, off is equal to other time. Next, negative edge trigger, on is 1 to 0, off is another time. Now we are going to see about SR latch. In SR latch, the complementary outputs are Q and Q dash. When Q is high, the latch is in set state. When Q is low, the latch is in reset state. For active high input SR latch, it is also known as OR gate latches. When R is high, and S is low, it is said to be reset state. When S is high and R is low, it is said to be set state. When both inputs are low, there is no change. When both inputs are high, then outputs are both low. It is said to be invalid. For active low input S dash R dash latch, it is also known as NAND gate latch. When R dash is low and S dash is high, it is said to be reset state. When S dash is low and R dash is high, it is said to be set state. When both inputs are high, there is no change. And when both input is low, the both outputs are high. It is said to be invalid. Drawbacks of SR latch. Invalid condition exists and thus must be avoided. These are the characteristics table of SR latches and S dash R dash latch. When both inputs are low, there is no change. When both inputs are high, it is in the invalid condition. In S dash R dash latches, both inputs are low, it is in invalid condition. Both inputs are high, there is no change. It is the difference of SR latch and S dash R dash latch. For active high input, if set is high and reset is low, then the output Q is 1 and Q bar is 0. If set is low and reset is low, then the output is Q is 1 and Q bar is 0. If set is low and reset is high, then the output Q is 0 and Q bar is 1. If set is low and reset is low, then the output Q is 0 and Q bar is 1. If both inputs are high, then the both outputs are 0. Gated SR latch. It is the combination of SR latch and enable inputs with two NAND gates. These are the logic diagram of gated SR latches. If output changes only when enable is high. These are the characteristics table of gated SR latch. D-latch. Gated D-latch is nothing but making reset input is equal to S dash. D latches eliminate the undesirable condition of invalid state in SR latch. This is the logic diagram of gated D latch. When enable input is high, that is D is high, latch is set. When D is low, latch is reset. Hence, when enable input is high, Q follows D inputs. This is the characteristics table of gated D latch. Next, we are going to see about latch circuit. Latch circuits are not suitable in synchronous logic circuits. When the enable signal is active, the excitation inputs are gated directly to the output Q. Thus, any changes in the excitation input immediately causes a change in latch output. The problem is solved by using a special timing control signal called clock to restrict the time at which the state of the memory elements may change. This leads us to the edge-triggered memory elements called flip-flops. Next, edge-triggered flip-flops. Flip-flops are synchronous bistable device. Output changes state at a specified point on a triggering input called the clock. Change state either at a positive edge or at the negative edge of the clock signal. These are the timing diagram of edge-triggered flip-flop. These are the logic diagram of edge-triggered flip-flops. The clock input is given directly to the positive edge, but in the negative edge, the NOT gate is used in the clock input. Next, we are going to see about SR flip-flops. It is on the triggering edge of clock pulse. When S is high and R is low, then it is said to be set state. When R is high and S is low, then it is in reset state. When both inputs are low, there is no change. When both inputs are high, then it is said to be invalid. These are the characteristics table of SR flip-flops. SR flip-flop has three parts: basic NAND latch, pulse triggering circuit, pulse transition detector circuit. The pulse transition detector detects a rising edge and produces a very short duration spike. These are the logic diagram of SR flip-flops. In the clock signals, we include pulse transition detector. Now we are going to see about D flip-flops. D flip-flop only contain single input D, that means data. When D is high, then it is set state. When D is low, then it is in reset state. The output Q follows the input D at the clock edge. If you want to convert SR flip-flop into D flip-flop, you should add an inverter. The application of D flip-flop is parallel data transfer. These are the logic diagram of parallel data transfer. Next, JK flip-flops. In JK flip-flops, Q and Q bar are fed back to the pulse steering NAND gate. It has no invalid state, include a toggle state. When J is high and K is low, then it is in set state. When K is high and J is low, then it is in reset state. When both inputs are low, then there is no change. When both inputs are high, then toggle occurred. These are the characteristics table and logic diagram of JK flip-flop. Next, T flip-flops. T flip-flops. It is a single input version of JK flip-flop formed by tying both inputs together. It is the logic diagram of T flip-flops and characteristic table of T flip-flops. Application of T flip-flop is frequency deviation and counters. These are the logic diagrams and timing diagrams of this application. Now we are going to see about asynchronous input. SR, D, JK inputs are synchronous inputs. These inputs are transfers to flip-flops outputs only on triggered edge of clock pulse. Asynchronous inputs affect the state of the flip-flop independent of the clock. Example, preset and clear. When preset is high, then Q is immediately set to high. When clear is high, then Q is immediately clear to low. The flip-flop is in normal mode when both preset and clear are low. These are the logic diagram and timing diagram of asynchronous inputs. If you have any feedback and comments, let me know in Manjuladevi AR at jjcet.ac.in. Thank you.